A fiber laser can hold a cut edge you could paint straight from the machine. When that edge goes rough, burred, and streaked, the beam is almost never the problem. 7 things cause it, and they show up in a predictable order. Here they are, most common first. First, the protective window under the cutting head. It is a thin lens whose only job is to stop spatter reaching the expensive optics. Contaminate it, and it absorbs energy instead of passing it. The focus shifts, the power at the workpiece drops, and cut quality falls off within minutes. The tell is drift. The first sheet of the shift cuts clean, and quality degrades as the window heats and clouds. If a fresh window fixes it instantly, the real question is why it got dirty. Too little standoff, piercing settings that throw spatter, or a cross jet that has stopped working. Second, the nozzle. It shapes the assist gas column that blows molten metal out of the kerf. Once the orifice is dinged, oval, or coated in spatter, that column goes turbulent and asymmetric. You get dross on one side of the part and a clean edge on the other. Related, and just as common, the beam not sitting centered in the nozzle bore. Even a slight offset pushes the gas unevenly around the kerf. Cut a small circle and check the edge all the way around. If one side is consistently worse, center the beam before you touch anything else. Third, focus position. The beam converges to a waist and the usable depth of focus around it is small, on thin sheet a fraction of a millimeter. Put the waist in the wrong place and the kerf changes shape. Too high and the top rounds over, too low and the bottom holds dross. Fourth, speed against power. Too fast and the melt front lags behind the beam, which is what deep angled striations down the edge are telling you. Too slow and you dump excess heat into the kerf, widening it, burning the edge, and leaving thick dross. The clean window between them is narrower than most operators assume. Fifth, the assist gas, pressure and purity. Nitrogen cutting relies on high purity gas to keep oxygen away from the melt. Let purity slip and stainless comes off the machine with a yellow-brown oxidized edge that will not weld or polish cleanly. On mild steel with oxygen, low pressure leaves dross and high pressure chills the reaction. 6. The material itself. Heavy mill scale, surface rust, oil, or a mismatched coating all change how the surface takes the beam, and thickness varies coil to coil. A parameter set that was perfect last month can fail on new stock. Blame the sheet before you blame the machine. 7th, the machine underneath. Worn slats, a part tipping into the bed, thermal distortion pulling a cut-off piece into the kerf, and pierce points that spatter into the following cut. None of these are laser faults. They are all fixture and nesting problems that leave marks the customer sees. So work it in order. Window, nozzle, and beam centering, focus, speed and power, gas, material, then the bed. Change one thing at a time and cut a test coupon after each. Chasing parameters before checking consumables is how a good machine gets a bad reputation. Next, nitrogen versus oxygen and the real cost per meter.